Hello, math analysis students. In this video, we are going to work on exponential applications, interest problems. We're going to write and solve equations involving compounded interest. Okay, so we have interest formulas. You do not need to memorize these formulas. Okay, when we ask you to solve something, we will give you these formulas, so you do not need to memorize them. The first is our compound interest yearly. FV, standing for our final value, equals P, our principal amount or investment, times 1 plus R, which is rate, to the T power. Our compound interest, which is FV, or final value, equals principal times 1 plus R over N to the NT. And our continuous interest, PERT, final value equals P times E to the RT. It's important to note that the compound interest yearly and the compound interest, they are not actually two separate formulas. If the interest is compounded yearly, where N equals the number of times per year, if we have R over 1, then that's just R over here. And if we have 1 times T, that would just be T. So this one is just a variation on this one specifically where N equals 1. Again, P stands for the initial investment or the principal amount. R stands for the rate as a decimal. T as the time. Now this must be in years. We will have some where they talk about months. We will need to convert that to years. And N is the number of compounding periods per year. And this one over here with continuous interest, we'll be using E, which is the irrational number. You don't need to know the amount. You don't need to know this limit definition. You just need to be able to locate it on your calculator. So let's get started here. Let's take a few moments and practice finding R, finding T, and finding N. I encourage you to pause the video and do these on your own, and then come back to it after you have completed these on your own. Okay, finding R, we're going to convert percents to decimals. So we always need to move our decimal place 2 units to the left. So 11% would be 0.11. 7%, remember this is 7 right here, we would need to move our decimal place over 2, so 0.07, not 0.7, that's 70%. This one, 3.75, we would move our decimal 2 units over, and we would get 0.0375. This one, we would move it 2 units over, and 0.01275. And the same here, move it 2 units, so 0.048. For T, remember T is in years. We have to convert our months to years. So 9 months, the easiest way to convert is probably as a fraction out of 12. 9 out of 12 is 3/4 of a year, or 0.75 year. 18 months, 18 over 12, that's a year and a half. That's 1.5 years. 30 months, 30 over 12, that's 2.5 years, or 2.5. 3 years and 6 months, 3 years and the 6 months is 1/2 of a year, 3.5. 2 years and 3 months, 2 years and 3 months, or 3 out of 12 months would be 0.25. And we're finding N, the number of compounding periods. If our interest is compounded yearly or annually, then N is compounded 1 time a year. Biannually, 2 times per year. Quarterly, so every quarter, would be 4 times per year. Monthly, 12 times per year. Daily, 365 times a year. If we did it weekly, that would be 52 times per year. Okay, now let's work out a few problems. Example 1. Suppose your grandparents invested $12,000 in an account paying 5.5% interest compounded quarterly when you were born. The money is to be given to you on your 18th birthday. How much will be in the account when you turn 18? Okay, so we're going to use this formula. FV equals P times 1 plus R over N to the NT power. I always like to list my amounts over here. F, V, P, R, N, and T. So the final value, that's what we're trying to find. How much will be in the account when you turn 18? That's what we're trying to find. P for the principal or the initial value. They invested $12,000. So P is 12,000. R is our rate, 5.5%. But remember, as a decimal, that is 0.055. N is the number of times it's compounded. It's compounded quarterly, so N is 4 times per year. And T is how much will be in the account when you turn 18, so after 18 years. So let's plug these in. We're trying to find the final value. So P is 12,000 times 1 plus 0.055 over 4, all to the power of NT, which is 4 times 18. Now you can simplify things here if you want to, or you can just go plug this straight into your calculator. I'm going to do this on the graphing calculator, and I'm also going to do it on Desmos just to make sure we know where to find all of the buttons. So first, if we want to plug into our graphing calculator, we would enter 12,000 times, let's do a parentheses, 1 plus 0.055 divided by 4, close parentheses, all raised to the power of, I'm going to put in parentheses just to make sure I don't mess up anything, 4 times 18, and then that gives us this value, 32,077.7343. Since we're talking about money, it makes sense to round this to the hundredths place, dollars and cents. So this would be $32,077.73. Now let's go over to Desmos and make sure we know how to plug it in there. If we wanted to enter the same thing, 12,000 parentheses 1 plus 0.055 divided by 4. Now let's make sure to close our parentheses there. All raised to the power of, and I would put in parentheses just to make sure we don't mess up anything, 4 times 18. And then we get that same answer right there, $32,077.73 when we round. So our value would be $32,077.73. It's a nice little chunk of change grandparents set aside for you. Follow-up question. How much more would you have if the interest was compounded monthly? So this time we would be using, and instead of being compounded quarterly 4 times per year, it would be at 12 times per year. So this time we would have 12,000 times 1 plus 0.055 over 12 to the power of 12 times 18. And when we calculate this, we end up getting $32,221.85. So how much more would you have? Well, this way, this is when it was compounded quarterly, when n equals 12. Excuse me, when it was compounded monthly, n equals 12. When it was compounded quarterly, the amount was $32,077.73. So how much more would you have if we subtract? Then we end up getting a difference of $144.12. So that's how much more you would have if it was in an account where the interest was compounded monthly. Let's do one more example. You invest $1,000 in an account that pays 4% interest compounded continuously. How long will it take for your investment to triple? So compounded continuously is a different formula. Final value equals principal times e to the RT. Okay, so how long will it take for your investment to triple? So our final value here, if we invested $1,000, our principal was $1,000, then triple means our final value would be $3,000. And our rate, it's 4%, so 0.04. And t, that's what we're trying to find. How long will it take? So we're trying to find t. So let's plug it. 3,000 equals 1,000 times e to the 0.04 t. Okay, so let's divide by 1,000. And we get 3 equals e to the 0.04t, which makes sense because triple. So since our t is in our exponent, we're going to need to get rid of this e down here. How do we get rid of e? By taking the natural log. If we take the natural log of this side, we have to take the natural log of this side. So the natural log of 3 is equal to the natural log of e to the 0.04t. So natural log and e cancel each other out. Remember, e is the base of our natural log, and e is the base of this exponent, so they will cancel. So the natural log of 3 equals 0.04t. And to get t by itself, now we just need to divide by that 0.04. So t is equal to the natural log of 3 divided by 0.04. Well, we want to actually figure that out, so let's just go over. I'm just going to go to my calculator. Let's see. The natural log of 3, close parentheses, divided by 0.04 gives us 27.46. So it's asking how long will it take for your investment to triple? So that is about 27.5 years. So about 27.5 years. And there we go. That's how to use our formulas and use the skills we have been working on with exponential and logarithmic equations to solve them. So bring your questions to our next class. Bye-bye.